Hello, my name is David Keuser, and it's my pleasure to present to you our work on GrandDetAuto, detecting malicious nodes in large-scale autonomous networks. This was a collaboration between the Aalto University and the Technical University of Darmstadt, where I also work. So to start off, let's talk about our motivation for this work. So we live in a world where there are more and more networks of devices that communicate with each other to collaborate. So one such example is a smart traffic scenario. Here cars communicate with each other to ensure a more reliable and efficient traffic. However, this collaboration is also based on the correctness of exchanged information. So if you take an example, the car on the top wants to take a turn. So it communicates with other cars to avoid any conflicts and avoid collisions in the end. However, if you consider that one of these cars might be compromised, then we get into problems, because this car can misreport its position, its trajectory, and then this could result in a crash. Of course, there are other scenarios where this might be much, much worse, such as on a highway or something like this. So our overall goal here is to detect adversaries. So one aspect that was important to our work is that we argue that true autonomy cannot rely on a central authority. This is also why the title, or the explanation for the title, Autonomous Networks. So we argue there are three reasons for this. One is that a central authority must always be available in the network, which cannot be always ensured. There are some applications where this might be problematic to rely on such a connection. On the other hand, a single authority is also a single point of failure and might be an attractive target for attacks. An example for this is our root CAs in PKI, for example. A third reason is, if you consider the smart traffic scenario, you have a couple of manufacturers of cars, and it seems politically hard for them to agree on a single common trusted authority that has the power to maybe shut down cars. So we want to avoid this. So if we look in the state of the art, there are a couple of interesting things. For one, there are these schemes that are called large-scale swarm attestation schemes. Here the idea is that the single trusted operator verifies the entire network in one go. They're very efficient. However, if you notice, there is a single trusted operator, meaning a single authority that can do things. So they are not really applicable to our autonomous networks. On the other hand, there are these thorough device-to-device validation schemes. They don't need a central authority, and they're very thorough and can detect complex attacks on the respective systems. However, they are also very expensive and are very hard to scale. It's kind of a n-squared problem, if you think about it, if you do it device to device. So a naive idea here would be to do the latter in a consensus. However, consensus also implies that it scales poorly for large systems. So overall, our goal here with our work is to close the gap, meaning detecting adversaries in a scalable and distributed manner. So first of all, let me give you the big picture of how GrandDetAuto works. In general, we have a network, and some node misbehaves. And some nodes in the network notice this and inform the network. So the network notices the suspicious behavior. Then the network randomly selects a jury. This jury then will individually verify the suspicious node, find a consensus only among themselves, and then inform the network about their verdict, about their decision, if the node is malicious or not. So the main idea here is to have a representative subset of nodes that we call jury to make the decision if the node is adversarial. And this results in quasi-constant scaling, because the number of jurors stays the same, even though maybe the network grows. Of course, quasi, because there's still communication overhead, and the larger the network, inherently you get more communication overhead in a mesh-like environment. So overall, we designed GrandDetAuto to be a kind of a framework. So under the hood, we require 4 components for GrandDetAuto. One such component is the integrity validation scheme. Here, you can use something like attestation using trusted hardware. So with attestation, we can detect some manipulated binaries or even some more sophisticated things. It allows one device to make measurements about the state of the other. Then we need the random election scheme that works in a distributed manner. Here, for example, is Intel's Proof-of-Elapsed-Time, which I will elaborate on later. And essentially what you need is a publicly verifiable randomness to distributively elect nodes. Third, we need a consensus protocol. Here, a traditional one is Byzantine fault tolerance, which guarantees honest outcomes if less than a third of the jurors are adversaries. Finally, we need to make some form of decision. So we all do this because different use cases have different requirements. And GrandDetAuto is adjustable to different use cases and requirements. So you can select different components regarding the need of the use case. And also we have some protocol parameters, which I will also elaborate on, to set up the scheme as you need it. So to demonstrate how GrandDetAuto actually works in detail, let's look at a simplified example. So in this network, D10 is actually malicious. And it sends some critical data to D7. D7 then can use remote attestation, in this case, to learn about D10's state. And it will notice, oh, something is wrong here, and D10 acts suspicious. Then it will announce this suspicion to the entire network. We call this blaming in this case. Because we cannot necessarily trust that D7 itself is not compromised and tries to blame a benign node or fake some evidence, we actually want to elect a jury to make this decision for us. So for the random jury election, it works a little bit like this. So each node throws the dice, so to speak. And because we want to elect 3 jurors inside of our jury, the best 3 dice rolls win, and they get to be the jury. This jury then also attests D10 and some data from D10. And in this case, because all jurors are benign, which might not be the case, they all find that the attested data is wrong. Find a consensus about this, because we don't want to rely on a single juror to make this decision, and they will reach an agreement. Finally, they will broadcast their verdict, their decision, to the entire network, and the network can then act accordingly. So let's look into the individual components in detail. For one, we have the integrity validation scheme. So in the literature, there are many schemes found that can detect misbehavior in devices. We already talked about remote attestation. There's, for example, static remote attestation, which can validate that the correct binary was used for something. There wasn't any manipulation of the binary that executes something. We also have more sophisticated versions of remote attestation called runtime remote attestation, which can also detect more sophisticated attacks, like runtime attacks. But there are also something like outlier detection. This is, for example, prevalently used in wireless sensor networks. Here we just find some outliers that are suspicious in reported values of other devices, some inconsistencies. And finally, there are also intrusion detection systems, which is similar to outlier detection, but works on a network level. However, because we have 2 parts in GrandDetAuto where we need an integrity validation scheme, there's also the possibility to use 2 distinct schemes and combine the advantages of different schemes. So for an example, let's say the initial blaming this thing where we find the suspicion, the initial one, we can do with an overestimating scheme, something like outlier detection, which is not maybe very reliable in a way, or we try to detect very rough outliers. And then the jury validation, so the validation that the jury does itself, we can do with a thorough scheme. So something like remote attestation. So the next component is the random election. Here we also have different options. However, we implemented a specific instance for GrandDetAuto for our evaluation, and we found a best fit. So I want to present to you this specific one in depth. So first of all, let's talk about Intel's Proof-of-Elapsed-Time. So this was invented as an ecological alternative to proof of work in blockchains to elect a single block proposer. So let me roughly outline how it works. So first of all, you need a publicly verifiable random number for each node. What you can do in a simplified manner is, for example, use the hash of the public key concatenated with the current round number, and then take some bits from this. So for example, 643. Then we use SGX, which is Intel's trusted execution environment, which can attest some execution, and wait for this time and attest this waiting. So for example, in this case, we wait for 643 milliseconds and create an attestation for this waiting, which is also called a waiting certificate. Then, when we finished waiting with this, we will broadcast this waiting certificate around the network. So overall, everyone does this in a network, learns about different numbers, and then in the end, the lowest/fastest number wins. Overall, the waiting approach reduces message overhead. So to demonstrate this, consider a different node that waited for 849 milliseconds, however, already saw the waiting certificate above and can tell like, oh, I have no chance to win. Actually, there's no need for me to broadcast. So ideally, there are very few nodes that actually broadcast their waiting certificate. However, Intel's Proof-of-Elapsed-Time is not a perfect fit right out of the box. So we implemented a custom election scheme that is based on Proof-of-Elapsed-Time. However, the main difference here, the key differences here, is that we elect a group, our jury, instead of a single node. So the challenge here is to have the network converge on the same list of jurors in a distributed manner. How we solved this, just to outline, we made a lot of measurements and tried to find a good trade-off between a reliable jury election while still having a short election, so we don't need to wait for long, and also avoid some unnecessary messages, as I said with the waiting approach. Unfortunately, I won't go in depth into these findings because of time. However, what you need to keep in mind that minor issues with this election scheme can actually be tolerated by the consensus. So if there is an inconsistent jury list where people cannot agree on, let's say, one of the jury members, this can be also tolerated by the consensus. Speaking of which, the consensus is the next component I want to talk about. And here I also want to specifically talk about one particular protocol that we implemented, which is Byzantine fault tolerance. So just as a quick introduction, Byzantine fault tolerance protocols are useful to find consensus in a distributed manner, so without a central authority, among nodes, even when some misbehave. Usually, this is executed over the entire set of members, so the entire network in this case. And if more than a third, but less than 2/3 of jurors deviate, we cannot reach consensus. So for example, if we have like a 50-50 situation, the consensus actually stalls. We cannot continue. However, in our case, in GrandDetAuto, we randomly select a subset of jurors. This means we also have the option to elect another jury instead if we stall, and then try again until we succeed. In a more formal way, you could say we treat a liveness issue as less problematic as a safety issue. However, of course, you might have already noticed, we can also get very unlucky and elect an adversarial jury. So if more than 2/3 of our jury are actually adversaries, then they can make bad decisions. So we looked at the security of this approach in terms of probabilities. So if you consider this graph, on the x-axis, we have the percentage share of adversaries in a network, and on the y-axis, the chance to elect an adversarial jury, so the worst case. In this case, the graph shows a jury size of 37. Now we have to set a parameter that sets our target security. In this case, we set the goal, the red line, that our chance to actually elect an adversarial jury to be less than 1 in a billion, which means we can tolerate around 4% of adversaries in the entire network. Now, the next thing we can actually adjust is the jury size itself. So we execute this on different jury sizes. And for example, if you take 100 jurors, then we can actually tolerate 11% of adversaries in the network. So the next thing we can do is actually increase the required safety quorum and accept possible re-elections or more re-elections. So what does this mean? Let's take an example. So here the graph is the same as before. It's a 2/3 quorum. However, now we increase the necessary safety quorum to 4/5. And you can see this is a dramatical impact on our probabilities. So if we look at another example of 52 jurors, again with less chance than 1 in a billion, we actually can tolerate 19% of adversaries in the network. However, we also need to consider a third graph, and this graph shows the average election rounds needed per election per jury. So in the case, in our example, this would be 19% for the red line, the 52 jurors, which would result in around 1.3 elections on average. Finally, we also need to talk about the decision. However, we consider this the actual decision, not only is the node adversarial or not, but the actual decision, what should happen with the adversary, we consider this orthogonal because there's a complex topic as well as very use case specific. So just outline you how this works. For example, we could just straightforward expel the adversary. However, if you consider our car example from the beginning, this might be actually a very bad idea. So you have like a bad car that is potentially dangerous and you cannot just ignore it. So in this case, it might not be a good idea. And on the other hand, there's also some literature and current research on self-healing and secure reset, which might also be considered for this. So finally, let's talk about the evaluation, where we demonstrate the efficacy and the efficiency of our scheme. We first set up a real-world network consisting on 10 nodes, a couple of Raspberry Pis that run opTEE. We implemented the protocol on these devices and also our custom election component. We then took a lot of measurements and also used a network simulator to see how well our scheme scales. In this case, Omnet++, with up to 100K nodes as a mesh network. So one of the measurements that is important to consider here is the communication delay between nodes. And we measured real-time delays between our experimental setup because they were communicating via Wi-Fi, and found, okay, there's a latency around like 3 to 80 milliseconds. So in our large-scale network simulator, we actually assign random latencies in that range. And finally, important to note is that the broadcast inside of the network simulator was implemented as flooding. Of course, there are better schemes like gossip that reduce the overall message overhead quite a lot. However, we wanted to avoid introducing additional randomness into our evaluation results. So finally, let's look at our evaluation results, and we measured this per phase. So you can see all the different phases of our protocol, of our GrandDetAuto instance, and you can see which one takes how long. However, consider, for example, the blame only shows the time when the last node has received the blaming broadcast. So there's a lot of overlap here, because some nodes receive the blame before others, and then overall they can already start with the election. So there's a lot of overlap. So these are just the end when everyone knows about things and is done with this phase. So for 100K nodes, in this case, we took a total runtime of, on an average of 42 seconds. Oh, these were averaged over 30 runs. However, note that the worst case delay between any two nodes in these networks was already on average 24 seconds. So what this means is these are the furthest nodes apart in the network to communicate with each other. So on the other hand, we also measured the average message count per node, per phase. And also note, this is why it's also important to consider that we use flooding. This includes forwarded messages. So this should give us a good idea of how much strain each phase puts on the network. And as you can see, by far the most message overhead consumed is by the election phase. However, this is a complete round of GrandDetAuto. And again, we can adjust some things to our needs. And because we have a BFT protocol, actually we do not have to re-elect the jury every round. So again, this is configurable, but you can decide, oh, if we have a valid jury, we can actually use this jury for 10 rounds before we do another re-election. This is very useful if you want to avoid some message overhead and also save on some runtime. Okay, that's from my side. Thank you. And now my live counterpart will take questions.